Okay, we will go ahead and get going. Last time we were talking about peanut butter. In the last couple minutes from class, I have here Skippy and Adams. We had a discussion last time as to whether it would be a good idea for me to take a picture of Jif peanut butter, format it as a .gif file. There was a discussion about whether that is pronounced Jif or GIF. There's people on either side, and then send it to my son and ask him to pronounce it or something like that. I think that's a little too esoteric, but I think you might enjoy it. In any case, Skippy versus this all natural atom stuff. You can't see it, but you can sort of come over after class and play around with it and watch the oil ooze around the top. The reason for that, as we discussed, and you look at the nutritional label, the natural stuff contains ingredients, peanuts, 1% or less of salt. And it says that there's 16 grams of fat and 3 of them are saturated. The peanuts says it contains hydrogenated vegetable oil from various sources. These used to have double bonds in them. Hydrogenation makes them so that they don't have double bonds in them. I'm not sure why that's not reflected in the fat versus the saturated versus unsaturated fats. Maybe if you hydrogenate it, you don't have to count it as saturated, who knows? But in any case, hydrogenation gets rid of the double bonds, replaces it with alkane instead of alkene. That then is a solid at room temperature and can more easily be stirred into peanut butter. Now, why would you want to do that in the first place? Well, we're going to get to that later today as we talk about radical chemistry. So just to orient you for the remaining, 6 lectures of the class, today we're going to talk about radical chemistry. That's the only new reactions we'll be dealing with from here on out. And then starting Monday, we're going to begin with analytical techniques that allow you to use data to determine the 3D structure of organic molecules. Is the wonky peanut butter any worse for you? No. In fact, there would be some argument that the unsaturated fats in the natural peanut butter are probably better for you than the hydrogenated ones. But I don't know if that's worth putting up with the slurry of oil and peanuts up at the top that you have to stir in every time. And there is a texture difference, honestly. Okay, let's see. So chapter 15 is about a class of molecules called radicals. And these are molecules with unpaired, either one or more unpaired electrons. Okay, this is a departure from everything we've done previously because all the reactions we've done previously have involved 2 electrons. 2 electrons on a heteroatom, lone pair on a heteroatom, or 2 electrons in a pi bond acting as a nucleophile, attacking an empty orbital. Here we're going to be talking about singly filled orbitals, and the chemistry will be a little bit different. They'll be able to do some things that the filled and empty, completely filled or completely empty orbitals are unable to do. So in organic chemistry, we are most interested in carbon-based radicals. So let's talk about the stability of various radical intermediates. I will point out that radicals are generally very reactive, very high energy, short-lived, meaning they don't hang around for long, and therefore are present in very low concentration under the conditions that we will be working in. Okay, radical stability, a tertiary radical, you indicate an unpaired electron with a single dot. All right, now if you look at that tertiary radical, I can draw in the CH3s that were implied but not shown, but on that central carbon you have 3 bonds to other carbons and then an unpaired electron. That is a neutral carbon, and by virtue of the fact that I've shown you the single electron, you know that it's a radical. If I had just shown you this, that would imply that a proton was there. If I show you this, I need a negative charge there. single electron, the carbon is neutral. But the tertiary radical is more stable than a secondary radical, which is more stable than a primary radical, which is more stable than a methyl radical. So radical stability tracks with what we learned about carbocation stability. So you can think of radicals as being electron deficient. They're kind of similar to carbocations, and therefore the things that stabilize carbocations like resonance or hyperconjugation should also stabilize radicals. In terms of radical structure, let's look at that tertiary radical. Generally, you can think of radicals as being planar. sp2 hybridized at the carbon that bears the unpaired electron. And you can think of that unpaired electron as occupying the p orbital on that carbon. Now, there's some evidence that radicals can pyramidalize. By that, I mean these three methyl groups on the outside might flap up or down with some equilibrium constant, but it's okay for the most part to think of radicals as being planar. And if we look at them this way, you can see the origin of the hyperconjugation that would stabilize the radical as a filled carbon-hydrogen bond can donate electron density into the half-filled p orbital. All right, questions so far about radicals? Resonance can stabilize radicals. So the classic example of this is an allyl radical in which the unpaired electron is shared between carbons 1 and 3. And in order to, I don't know if you remember at the beginning of the semester, we talked about pi systems and the 3 pi orbitals of the allyl system, pi 1, pi 2, and pi 3. The unpaired electron is in the pi 2 orbital that's only on carbons 1 and 3, but never on carbon 2. Is that looking vaguely familiar? I'm not drawing everything out, but that's the idea. Okay. So let's see. Let's talk about the kind of chemistry that generates radicals and that the resulting radicals can in fact do. So to make a radical, they call this radical initiation. That sounds like maybe being inducted into a far right or far left militant organization, then Homeland Security might be interested in that. But in reality, this is just breaking a sigma bond, okay? How do you break sigma bonds? Well, you've got two strategies. You can use UV light to promote an electron from a bonding orbital to an anti-bonding orbital and then break a bond. Or you can use heat to increase vibrations in the bond to the point that the spring snaps and the two atoms end up far away from each other. A typical scheme for initiating radical chemistry is to start with something that has a weak sigma bond. The bond between bromine atoms in Br2 is weak. That's why we use it as an electrophile. And if you add UV light, you can make the bond break. Typically, organic chemists don't want to write out add UV light over the arrow. So they will instead use the abbreviation H, Greek letter nu, where H is Planck's constant and nu is frequency. Some people that don't like to write Greek letters will use HF, where F is frequency. Either way, this just refers to a photon of UV light. So when you see that, it doesn't mean anything. Don't panic. You're not going to have to grab your calculator or do anything with energies. It just means you're adding UV light. And if you want to not draw the Greek letter and just use the Roman letter V, that's fine too. That excites an electron from the bonding to the anti-bonding orbital. The bond breaks, and either atom that was involved in the bond originally takes an electron away. That's called homolytic bond breaking. And that takes something that did not have any unpaired electrons and generates two radicals. You can also do this with heat, and there are a class of molecules called peroxides where the R group is hydrogen or some hydrocarbon. The oxygen-oxygen sigma bond is also weak. Instead of writing add heat, organic chemists will use the Greek letter delta, which I don't know, looks maybe to them like a fire if they squint at it. And so I don't know. Adding the heat takes the bond vibration and makes it happen to a larger extent. And if you get the two atoms far enough away from each other, the bond breaks, the spring snaps, and they each go away with an electron. We'll draw arrows for that in this fashion. And I should pause here to talk about how we use arrows when we're doing radical chemistry. When we used to do, say, SN2 reactions, we would use an arrow with two little flags at the end of it to indicate motion of two electrons. Now that we're doing only one electron, we're using an arrow with sort of a fishhook head. That is, there's only one flag instead of two. That's an important difference. It's one that you should remember and be able to use and be able to recognize in mechanisms. If you use the wrong arrow, the mechanism isn't correct. Okay, so radical initiation is one of the ways that we generate radicals, and there's tons of different molecules that'll do this. I'm only showing you the two that your text shows, but there's a whole host of other ones. And if you work in an organic lab, particularly Professor Castle's lab does radical chemistry that is radical in the sense of being cool, but also radical in the sense of having unpaired electrons. You might encounter some other radical initiators. Another kind of chemical step that happens is propagation. And this is where one radical reacts with something to generate a new radical. Okay, I should point out that these reactions are not high yielding because you're generating something that's very high in energy. So most of the time when a molecule absorbs a photon, it just relaxes without breaking the bond. So any of these radical initiation steps result in a small concentration of radicals. In other words, most of the starting material is still Br2. There's only a few bromine radicals present. Propagation steps, what do we mean here? Well, let's imagine that you take this hydrocarbon and you generate bromine radicals in the presence of the hydrocarbon. What can happen next is a mechanistic step called hydrogen abstraction. It's not deprotonation because removing a proton is a two electron thing, right? Lone pairs attack a proton and the carbon hydrogen bond breaks. In this case, a single electron will attack the proton, stealing it away with one of its electrons to create a new hydrogen bromine bond. This is a new mechanistic step. We haven't done this before. We aren't really going to worry about what's going on with the orbitals here, though if you want, you can think of the single electron on Br being dumped into the carbon hydrogen sigma star, and then another electron from the carbon hydrogen bond coming to make that a new bromine hydrogen sigma bond. What's left behind on the carbon that used to have the hydrogen that we abstracted is an unpaired electron. Now, some people will actually use an arrow here with the hook to indicate, oh, that electron stays on the carbon. You can do that. I just find it redundant by virtue of the fact that I showed making a new sigma bond with a half-headed arrow on both hydrogen and Br. I know there's an unpaired electron left behind. Okay, so that's pretty important. It's called a propagation step because you started with a bromine radical, you ended with a carbon radical, one radical in, one radical out. Questions so far? That's pretty important. Anything you want to ask about that? Okay. Another type of propagation step involves a carbon radical reacting with an electrophilic reagent. So the carbon radical can find bromine, and that will create a new carbon bromine bond and then regenerate the bromine radical. All right. Notice in both of these steps, it's very common for one radical to react with another molecule that is not a radical. The reason for this is that radicals are only ever present in fairly low concentration. So the odds of two radicals finding each other are small. Also notice that we've sort of got two steps of a chain reaction here. We generate a small amount of bromine radical. We trade that via hydrogen abstraction to make a carbon radical. Then that carbon radical reacts with some of our remaining starting material to generate this product and another bromine radical. And then that bromine radical is going to be surrounded by a bunch of other starting material molecules. And so we will just go from step 1 to 2, and then from 2 back to 1, and so on in this chain of reactions. So unlike two electron mechanisms where there was a beginning and an end, in this reaction there's an initiation step and then a cycle of propagation steps until you run out of material to work with. The course of the propagation steps is one eternal round, I think. Yeah.
What do you mean by running out of material? You just, like, would that decrease in concentration over time, or do you mean that?
Yeah, well, let's imagine that I have, the question is, what do I mean by running out of material? Let's imagine I do this reaction using UV light. Suppose I have, 1 mole of, hydrocarbon and maybe 1 mole of bromine, something like that. I don't know, maybe I'd want half an equivalent, I don't know. I'm never forming more than just a small amount of bromine, right? And so, of the bromine radical. And so at first, bromine will be surrounded by either other Br2 molecules or by cyclohexane. If bromine is surrounded by another Br2 molecule, that will result in a propagation reaction that is reasonable, but that we can't tell because we just traded one radical for another bromine radical. But if it happens to be next to, I'm sorry, my nose is itchy. Story of my mother's life for the first 4 or 5 years, or maybe more, I was always whining about having an itchy nose. She just hated itchy nose. She hated that, but I still got it. So anyway, sorry. But if that bromine radical is near a hydrocarbon, it can do hydrogen abstraction, and that will generate this carbon radical, which is present only in a very small amount. If that hydrocarbon radical is near another hydrocarbon that's not a radical, we're going to do just the same thing we did above with bromine. That is, we're going to trade one radical for an identical radical. And so that's going to be sort of a silent background process. But at no point is the concentration of the radical very high. But if that radical happens to be around Br2, it can do this step and generate another Br radical. So these radical reactions are characterized by a lot of different things that are possible, but only some of which are productive. Okay. And that's where we are. Of all our options that are likely, only these two result in a product. Everything else just regenerates starting material. So we continue to crank on this until the amount of starting material starts to decrease. Go ahead.
I was just wondering, because we have a carbon radical right here, is there going to be any point in which we have two carbon radicals that form a bond?
Yeah, so your question is a great one. It is, as the starting material starts to deplete and all we've got present is radicals, or if the radical concentration increases, can radicals start to find each other and react with each other? And the answer is yes, though those steps are rare because they only happen at the end of the reaction, and because radical concentrations are small, it takes a long time for two radicals to be in the right situation to find each other. But yes, when that happens, you could create some of this, and that does happen, but it happens in such a small amount that we generally ignore it. Similarly to Br radicals could recombine to generate Br2, and then similarly one Br radical could encounter a carbon radical to generate that product. Now, some of you may be wondering, and I forgot to address this in the beginning class, or the class at noon rather, why doesn't the Br radical remove a hydrogen from a molecule that's already been modified with Br? Why don't you get subsequent modification? And it turns out if you want to do that, you can run the reaction in a way that will, completely modify the molecule, but there are experimental workarounds that allow you to stop at adding the single bromine instead of multiple. We won't talk about how to do that. It's a practical issue. We'll just assume that that's how we're doing things when we do this reaction. So if I gave you this hydrocarbon as the starting material, the appropriate product is this one. And this is the first example of what we would call a CH functionalization reaction. We're taking a hydrocarbon with nothing but fairly unreactive CH bonds and replacing one of them with something that's a good leaving group that we can now go on to do a whole host of other things. These CH functionalization reactions are highly useful and highly sought after because they allow you to take fairly inert starting materials from hydrocarbon starting materials from petroleum sources and convert them into more useful commodity chemicals. All right. Questions so far about that mechanism? Go ahead.
So basically, we're just pumping UV light into those starting materials until all of it becomes a radical?
Yeah. We're pumping UV light in until we've consumed all of our starting material. We have an appropriate yield of the desired product. Others? Yeah. Would it slow down if it were a less stable radical?
Yeah, so for example, methyl versus the tertiary.
Yes, you would think that the reaction would be slower for a less stable radical. And this is actually why radical bromination is selective, regioselective. So if we modify this cyclohexane starting material with a methyl group, we've got all kinds of different hydrogens here. 4 different kinds of hydrogens, which I'll try to highlight in color just so that you can see that they're different. 3 of them are secondary, 1 is tertiary, and the other is primary. Uh-oh, run out of colors, oh well. Now, I'm not going to draw the radicals that would come from abstracting either of these hydrogens. Can you see that if we abstracted the pink one, that would be a primary radical? If we abstracted the purple or the yellow or the green ones, that would be a secondary radical. That's less stable than if we abstracted the orange one. If we abstract the orange one, that leads us to the more stable tertiary radical. So we preferentially form the more stable tertiary radical, which then in the second propagation step allows bromine to be installed at the tertiary carbon. So the product for this reaction is only the one where bromine is at the more substituted carbon. So radical bromination is regioselective for going through the more substituted radical. Notably, we don't observe any bromide products where the Br is at the green, yellow, purple, or pink positions. The more stable, the tertiary radical is more stable because of hyperconjugation. All right, questions? So this principle, go ahead, sorry.
Yeah, for the termination step, I know it's rare, but is there going to be any point in which, like the double, I think that's what it's called, rings, the cyclohexane
Yeah.
rings. Is there going to be any point in which we need to get rid of those because they could be harmful, or like how we?
Yeah, so the question is, we're going to form a small amount of this. Is it enough to worry about? That's a practical issue I actually don't know about. In any chemistry, in any chemical reaction, you have to have a way to separate the desired product from undesired products, byproducts. In this case, the polarity would be different. And so there's a chance you could separate the desired product from undesired termination product through chromatography or distillation. And in fact, it might be present in such small amounts that it really wasn't worth worrying about. Okay. Is the product with Br on the tertiary carbon the only product? Yeah, that's the only product we would show. I'm going to hedge and say, do the others form? Probably depends on how careful you are. Do you ever get free radicals on primary carbons? Yes, you can. So unlike primary carbocations, primary radicals, I think are not unreasonable if that's the only choice you have. But if you have other choices for bromination, you're going to choose the one that gives you the more stable radical. Okay. Another part of radical selectivity, another way you can influence it is to react in a molecule with a double bond. The most stable radical here would be the resonance stabilized one, so that if you did radical bromination here, you would selectively remove the hydrogen, abstract the hydrogen that's on the allyl carbon, so that you could generate the resonance stabilized allyl radical. Now, fortunately, carbons 1 and 3 are identical to each other here, so it actually doesn't matter which one which resonance structure we react from. We can, oops, I used the wrong arrow. We can attack bromine from carbon 1 or from carbon 3, and it doesn't make any difference. If they were different, you would simply consider the radical reaction from either resonance structure. But that's going to install the Br at the allylic position. And therefore, we call this allylic bromination. It's not a new or separate reaction as far as I'm concerned, because it simply involves making the most stable radical you can, and then getting the final bromide product as a result. Okay, other questions? Yeah.
Are we gonna have to reflect stereochemical changes as well?
Are you going to have to reflect stereochemical changes as well? I've shown you, yeah, I mean, stereochemistry can be an issue because radicals are planar, they could attack from above or below. So in a case where I generate a stereo center, then yes, I'm going to get both configurations. So that was what was indicated by what I drew, but you could also be maybe a little bit clearer by drawing that. Yeah. Okay. Allylic, let's see, the susceptibility of allylic carbon hydrogen bonds to being abstracted by radicals is one reason why you would want, if you're a food manufacturer, you would want to use the hydrogenated oils instead of the oils that have double bonds in them still. And I talked about this last time, and I think one of you was passing around a vial that had some oil that was fairly old in it, and you were smelling the rancidity. What's going on there, I'm going to show you just the tail of fatty acid chain. This is from linolenic acid. And you have carbon hydrogen bonds at these allylic carbons. And if you had a radical, you could abstract that hydrogen to generate a resonance stabilized carbon radical. And in fact, this happens in air because we are surrounded by about, I don't know, 20-ish, 20, 25, I forget what the number is, % oxygen. Now, you may have learned to draw the Lewis structure of oxygen like this, and that's fine, but that doesn't capture what the MO picture of oxygen tells you. And I don't know what all the orbitals down here in energy are, but the highest orbitals in oxygen are this pair of equal in energy orbitals that each have a single electron. Now, most of the time, the electrons have parallel spin, and that's a fairly stable arrangement. You've maybe learned about Hund's rule in general chemistry. Having parallel spin is called the triplet state or triplet oxygen. And triplet oxygen, thankfully, is fairly unreactive. However, and that's why we are not currently on fire. However, if you excite oxygen, you can cause a change in spin state. This is the singlet state or singlet oxygen. The overall spin on the molecule is 0. One spin is up and the other is down. And this is very reactive. It reacts like a diradical. So instead of drawing the Lewis structure like this, I mean, it doesn't quite capture all of the features, but you could draw the structure of singlet oxygen like that, and that would communicate that you've got a diradical. And so it's very easy for singlet oxygen to abstract a hydrogen. You get that radical. You would form as a byproduct the hydrogen peroxy radical or hydroperoxy radical, which could then, because it's so nearby, react with the allylic radical that we just made. And that would install the organic hydroperoxide. And this can go on through later reactions, which I'm not going to show you, to generate just the regular hydroxy group on that carbon. And that's fine, but that smells and tastes bad. That's the rancid taste you can detect in things like that are not hydrogenated oils, oils with double bonds that sit around for a while. So that's why people would want to make Skippy instead of this, because you don't have to worry about allylic radical reactions with Skippy because there aren't as many double bonds in it. All right, so it's typically an issue of shelf life. Other questions you want to talk about? Yeah.
So why is having two better than having like one up and one down? Like why does that make it a singlet versus a?
Yeah, why is the parallel spin state less reactive than the singlet spin state? It has to do with quantum mechanics. There's a term in the Schrodinger equation that's called the exchange integral, where two electrons that are parallel to each other experience some stabilization. Any more detailed explanation would require me to review my notes from 552 in detail and write some equations, which I don't really have in my brain anymore. It's just gone. So sorry. Everybody's okay with that. The other two places you can encounter radicals in your life are in making plastics and then in combustion. So our ancestors have been burning things for like ever. For as long as there have been humans, there have been burning things. I don't know. I don't know when fire was first discovered. Who knows? Anybody know the history of fire? Since prehistoric times, from the beginning of time. Anyway, fire has been an issue. Fire is itself a radical reaction. So I want to show you just a few of the reactions that are occurring in combustion. Now, combustion's complicated. It's mostly studied by engineers. You may have learned about combustion in general chemistry where they told you, well, if you have methane and oxygen, you can generate CO2 and H2O. Go ahead and balance the equation 2 here and 2 there, or something like that. I've seen that before, and there's free energy release. But there's a ton of stuff that happens. This is just a starting equation and an ending equation. There's a ton of stuff that happens between here and here. By the way, George at home Googled and says, claims for the earliest definitive evidence of control of fire by a member of the Homo group range from 1.7 to 2 million years ago. Evidence for microscopic traces of wood ash begin about 1 million years ago, has scholarly support, and that is from Wikipedia. Okay, so for 1 million years, humans or organisms like humans have been burning stuff. Most recently, the young men in our ward. Oh, I should tell you about, no, well, why not? Stories take up time, but so a few years ago, and the friendship sort of petered off, but there used to be my oldest son, Nate, was friends with a kid that lived nearby, and they were sort of into building things and or doing cool things that they found on YouTube, which isn't always the smartest thing to do when you're a teenage boy. So this friend came and said, "Hey, Nate, I learned on YouTube how to make napalm. You just take gasoline and mix it with styrofoam, and it creates a sort of jelly that burns a long time." And of course, they weren't going to be defoliating any forests or firebombing people, but they decided to try to light off this sample of napalm at exactly the time that we were having a bunch of people from the ward over. It was one of these get to know your neighbors kind of experiences. And there were all kinds of little children, 3 and 4 year olds gathered around in the front yard around this paint can on which they had put the paint can lid on which they had put some of the napalm, lit it off, big flames, thick black smoke. And Nate at that point did not understand why I was upset. I mean, what could happen, Dad? Oh, I don't know. The 2-year-old near the fire, that you can't think of anything that could happen. But it wasn't my fault. I don't care. It was on my property. Anyway, so that was an example of combustion. I don't know. That's all it had to do. But the mechanism is actually kind of complicated, though I did want to show you just a few of the radical reactions that happen, because I think if you're going to start a fire and look into the flame and think it looks nice, you ought to have an idea of what's going on. So understand that combustion is a chain reaction, just like all radical chemistry. And so we're not going to worry about how it starts. There are a bunch of radicals that are available. For example, singlet oxygen is an available radical. And in fact, one of the reasons you need to add heat to get a fire going is so that you can make singlet oxygen. Other radicals that are present include the hydrogen radical, the hydroxy radical, also even just a single oxygen atom. All are sort of present in the flame. So if you start with methane, one of the first things that can happen is hydrogen abstraction. And so we'll show this happening from the hydroxy radical, but it might happen with any of the others. We simply abstract a hydrogen atom that creates a molecule of water, and it creates methyl radical. And then I was looking at a paper where engineers and chemists have been studying this mechanism, and there are like 10 to 15 different things that happen after this point. I'm going to try to show you one of them that generates CO2. And I'll try to, we'll try to do it in a way that doesn't stress anybody out too much. I don't see myself clearly asking questions on an exam about stuff I barely understand, but I would expect you to recognize this as a hydrogen abstraction step, and this is a propagation step. The methyl radical could react with just a single oxygen atom. This sort of looks like a termination step, which I said were rare, but remember that fire happens at, like, depending on whether it's wood or natural gas. Methane, I think, burns, the methane flame is about 1900 degrees Celsius. So a lot of things that we wouldn't do at room temperature can happen at that elevated temperature. You make a new carbon-oxygen sigma bond, but you still have an unpaired electron on the oxygen. And then this wild thing happens. We make a carbon-oxygen pi bond, and we spit out a hydrogen radical that can go on to do other things. And we just made formaldehyde. Another reason why you probably don't want to smoke is because you're going to be breathing in, among other things, formaldehyde. What else happens there? The hydrogen radical that you make can abstract a hydrogen from formaldehyde. Gradually, each of these steps should decrease the number of carbon-hydrogen bonds and increase the number of carbon-oxygen bonds, because that's what oxidation means. Then this, let's see, intermediate can actually spontaneously lose a hydrogen radical, and the molecule we just made has a name, and it's called carbon monoxide. So you generate carbon monoxide, which you don't want if you don't do combustion completely. And then through a couple of other steps, which, I mean, if you really want to see them, we can use a hydroxy radical with one of the electrons of carbon monoxide to generate the following molecule. And then all it takes is this to spit out CO2 and another hydrogen radical. So imagine all the work you'd have to do. I mean, we took, yeah. Oh, we've not been recording anything in there, have we? Oh, well. We took a single molecule of methane and we made CO2 out of it, but this isn't a balanced equation. We got lots of other things we haven't accounted for. And so this can be a very complicated process. But this is among the things, these are among the things that are happening whenever you light a fire. Speaking of fire, what is your guys' opinion about birthday candles and blowing them out?
The fact that you spit all over the cake before you eat it.
Yeah, don't you think we should sort of kill this? I mean, it's kind of sad, but so maybe you cut the cake first and then you blow off the candles in a corner by yourself while everybody else stands more than 6 feet away and sings to you. It's kind of not fun. Go ahead.
My last birthday, my aunt had me use
A hair dryer, okay. Or a leaf blower. Anyway, that's neither here nor there. Amber likes to pinch the candles out. I've never been able to get myself to try that. I'm afraid I won't do it quickly enough and then I'll end up with a blister. So. Oh, in George's family, the cake always has powdered sugar, which makes no sense because then that goes everywhere. So not only are you transmitting germs, but you're blinding people with the powdered sugar. Abolish birthdays? No, birthdays are fun. Actually, yeah, why do we celebrate our birthdays? Why does the mom who did all the work have to give presents to the child on the birthday? It seems like it should be thanks for birth, Mom. I don't know. Okay, the next place you'll encounter radicals, and we'll just have a bit of time to get started here, is in polymers. So there's a process called radical polymerization. Many of the plastics that you're used to and that you can recycle that are around you every day are derived from a radical polymerization process. One that we will talk about today and next time is polyvinyl chloride, or PVC for short. If you've used records to play music and people have said, oh, dude, I've got this sweet vinyl. They're talking about something that's made out of this polymer. PVC, though, you may have heard of in terms of like plumbing pipes. It tends to be fairly rigid. It's composed, you get it from the starting material vinyl chloride that just has chloride at the vinyl position. And it's a polymer where the red is going to indicate bonds between individual vinyl chloride subunits, where you have 2 carbons and then a bond, another 2 carbons and then a bond between subunits, another 2 carbons and then a bond between subunits, and so on. And how long the polymer gets is a function of the reaction conditions and the amount of radical initiator you use to get the reaction going. If any of you have ever used PVC pipe, it's fairly rigid. This is why it's important to blow out your sprinkler system in the winter before it freezes, because if you don't, the PVC pipe won't be able to expand as the water expands, and the PVC pipe will get shredded, by which we don't mean like, dude, you're shredded, but literally shredded in a spiral pattern. I know this because it's happened to me. And then I turned on the water for the sprinkler, and there were great floods of water coming up from underneath the lawn. And so anyway, that has to do with the properties of the polymer and my own stupidity with my sprinkler system. We'll talk about the radical mechanism that forms this thing next time. Guess we're out of time. So there we go. Have a good weekend. Enjoy General Conference.